Anna Schenfisch talking to us about ordering topological descriptors. So
thank you.
Yeah, take it away.
All right. So I'll just begin by acknowledging this is joint work with Brittany Fazy, David Millman, and Sam Mika. So today I'll start by introducing some of the main ideas I'll be using, so including lower star filtrations, which Tatum already introduced somewhat. And then we'll move into what it might mean to have a relation on different types of topological descriptors and defining that. Then we'll introduce the poset that we have so far and then discuss improvements we think we can make to our results and other questions that we have. All right. So as I mentioned, today I'll mostly only be thinking about lower star filtrations. So this is a type of height filtration where you pick a direction, say the one indicated by the arrow, you're filtering over some underlying simplicial complex, which is shown here in light gray. And at every height, you're recording the simplicial complex that happens at or below that height, the lower star, right? So here we see one vertex in our subcomplex. Here we have the edge. We see another connected component appear, and so on. We can filter our way through this space. We eventually see cycles and the deaths as connected components merge. And then past a certain point, of course, nothing else interesting happens, and that's sort of the end of the filtration. Okay, and just a quick comment. Here I've drawn these dotted lines lying flat just to help with visualization, and I may call them filtration lines. That's just a really nice way to sort of build geometric intuition for what's going on. Okay, so the topological descriptor that I think is the favorite of today and has been the favorite for many years is the persistence diagram, right? So just a quick recap, right? We have an axis corresponding to the birth of events and an axis corresponding to death events. And we have this record of birth-death pairings. And yeah, throughout the filtration, we're recording the homology of these subcomplexes throughout. Okay, so if you looked at this diagram, perhaps you were asking the question, why have I included these on-diagonal points, right? That's not something we typically see in a lot of instances of persistence diagrams. And so there's a really good justification for including these on-diagonal points. And it all comes down to the fact that they're usually actually computed, they're just omitted. So just let's revisit what is the sort of pipeline of the normal algorithm for computing persistence. So normally we begin with this total order of all the simplices in the complex, and the order is what's called compatible with the filtration. So if a vertex A appears before a vertex B in the filtration, in the index filtration, that ordering will stay the same. The index filtration is just sort of stepping out the underlying filtration simplex by simplex. Only a single simplex is added at a time. And from there, we get the boundary matrix, right? That tells us sort of the face-coface relations of codimension 1. And then we can reduce that matrix, and then the output of this algorithm is then the Betty numbers and all the birth-death pairings. And what this includes, these on-diagonal points, these instantaneous events. Okay, so let's focus in on this picture before we look at the words, right? What would an instantaneous event? So let's look at this sort of lowest on-diagonal point. Well, that corresponds to, in the index filtration, we see this vertex appear before the edge sort of immediately fills in and kills off that extra connected component. So we see an immediate birth and death of a connected component. Okay, so if we choose not to omit this probably already computed information, we get what you might call an augmented persistence diagram. So augmented means we have these instantaneous events recorded. Non-augmented means perhaps we're choosing to omit that information. Okay. And more generally, as we move to different types of topological descriptors that I'll describe, I think in the next slide, we have the same idea of augmented versus not. And that's whether or not they contain information about instantaneous events. Yep, so there's, if that was a lot of words, here's kind of the slogan to keep in mind. Augmented means that there's an event at the height of every vertex in particular. Okay, so two things to notice. First, notice that if we took a lower star filtration in a different direction, we would have gotten an entirely different diagram, right? And then also notice that for persistence diagrams, we're choosing to keep track of homology, but we could have chosen to keep track of any topological invariant. So for example, like Euler characteristic or Betti number are two things we also could have kept track of. And those would be other summaries of the shape, but just a slightly different summary. Okay. All right, so that last bullet point gives us lots of different possibilities for descriptor types. And so I'm going to be focusing on 6 in particular. So I have the Euler characteristic curve, which is where we record the Euler characteristic of a filtration. The augmented version that includes these instantaneous events. The Betti curve and its augmented counterpart. And then lastly, the more familiar persistence diagram and augmented persistence diagram. So that gives us 6 different ways of creating this summary of a simplicial complex through filtration. Okay, just a disclaimer, all the complexes that I'm going to be talking about, they have some general position assumptions, mostly related to collinearity. So that's good to keep in mind. Okay, so I have these 6 different types of descriptors. What would it mean to compare them or order them? Okay. So in order to define the relation, we also first need this definition called faithful. So this adjective describes a set of descriptors taken from multiple directions. So we say that a set of descriptors is faithful if there's only one simplicial complex that could have generated that same set. So let's go through a quick example of what's going on here. So suppose that our simplicial complex is just a single vertex, and that's a pretty good starting place. So here I have it drawn down here. And let's kind of dig into what would we need in order to create a faithful set of, let's start with augmented persistence diagrams. Okay, so suppose we take our first filtration, our first diagram we create by filtering in this upward direction. Okay, so we see one connecting component at this height, and we know that there are no other vertices because there should be an event at every vertex height. We only saw one event. So we know that somewhere along this line, there's a vertex, but we don't know quite what the coordinates are yet. We know the y coordinate perhaps, but we don't know the x coordinate. Okay, so maybe then we filter in this direction, right, this sideways direction, and then now we are able to pinpoint the exact coordinates of where that vertex is. And that's where you could use this word reconstruct, right? If I hand you these 2 diagrams generated from the basis directions, that's enough information to tell me exactly what the underlying simplicial complex was. Okay, now notice this is, we've been talking about augmented diagrams. If we switch now to non-augmented persistence diagrams, the story is slightly different. So notice that, say I came with these 2 directions, I would have still seen a connected component appear at the height of the vertex, but I haven't really confirmed that there's nothing living over in this quadrant. That quadrant sort of remains unexplored, right? We can't say for sure that there's nothing there because being non-augmented means we don't necessarily have an event at the height of every vertex. So in order to rule out this possibility, we would need a 3rd direction, such as this one, that kind of squashes down that unexplored region. And then we can definitively say, okay, there's a single vertex and here's its location. So for non-augmented persistence diagrams, we actually need one more to create a faithful set. Okay. All right, so that now we're ready to define the relation. So suppose we have 2 different topological descriptor types, so I'll call them A and B. And we say that A is less than or equal to B if we have some simplicial complex and we have a faithful set of type B. We can always find, sorry, sometimes I get this backwards. Yeah, if there always exists faithful sets of type B that are smaller than or equal to the cardinality of faithful sets of type A. So in some sense, B is more powerful than A. You sort of need less of type B to form a faithful set. Okay. Okay, so a good question to ask is this relation going to be well defined? And the first concern that might cross your mind is, what if you have a simplicial complex and it's just impossible to form a faithful set of descriptors? So there's a lot of related work that supports the claim that a faithful set is always going to exist. Tatum was talking about the persistent homology transform, and I've left that word off of the slide so I didn't have to define it, but that's exactly what's at the heart of most of these results, right? So in this first paper, Turner et al., they showed that if we take the uncountable collection of persistence diagrams from the entire sphere of directions, that forms a faithful set, okay? So there's at least an infinite faithful set. And then I think in 2018, Curry et al. Gave a bound on the size of a faithful set of persistence diagrams, and that assumed some curvature bounds on the underlying simplicial complex, so sort of like the flatness of it. And then our group at MSU, first we found an explicit description of a finite faithful set using augmented persistence diagrams for graphs, and then we later extended it to arbitrary simplicial complexes. And that was for augmented persistence diagrams and augmented Betty curves. And an interesting ongoing project is trying to kind of pin down the details of what we would need to extend that to augmented Euler characteristic curves. Okay, so we know that a faithful set always exists, at least an uncountably infinite one. And these results show that there are, in fact, finite faithful sets. The other issues related to well-defined, and this I've left as an exercise. It's kind of fun to go through and see, yes, it is transitive, yes, it's antisymmetric, etc. Okay, so we have our set, we have a relation. Let's see then if we can begin to order them. So there are a couple of really immediate results. The first is the following. It says that if you have a descriptor type, it's always weaker than its augmented version. And intuitively, that makes quite a lot of sense, right? If you have a faithful set of non-augmented descriptors, and then you add in the extra data of the augmentation, adding extra information isn't going to make the results any sort of less informative, right? So you have sort of this, you can think of it as like a forgetful functor from augmented, non-augmented. You have this sort of reduction from something that's more powerful to something that's less powerful. Okay. Yeah, it can be reduced to its non-augmented counterpart. And then in a similar vein, we have other results from this reduction idea. So we have the ordering that Euler characteristic curves are less than or equal to Betty curves, which are less than or equal to persistence diagrams. And the argument for this is also through reduction, right? So if I hand you a persistence diagram, well, then from that, you can immediately read off the Betty numbers, right? And if you know the Betty numbers of filtration, you could take an alternating sum and report back the Euler characteristic curve, right? So we have these reductions kind of going downstream that give us the relations as shown. And a nearly identical argument works for these augmented descriptors. Okay. All right. So far what I've described is a partially ordered set of my set of 6 descriptors. So we have everything that's not augmented is weaker than its augmented counterpart. And that's just the reduction of forgetting the information of the augmented data, or the on-diagonal points or the instantaneous events. And then we also have the ordering where persistence diagrams are stronger than Betty curves, which are stronger than Euler characteristic curves. And similarly for the augmented side. Okay. So let's go now into a little bit of discussion about future work and what I think is possible. So we conjecture that persistence diagrams, so non-augmented, are strictly less than augmented Euler characteristic curves. So why would this be a reasonable conjecture? So first of all, what does it mean for 2 descriptors to not be equal? In our setting, it essentially means you can find a simplicial complex where the faithful sets have different cardinalities. And we already saw an example earlier today, right? When we had a single point in R2, remember we required 3 persistence diagrams to form a faithful set. And I suppose I went through that example using augmented persistence diagrams, but the same argument holds for augmented Euler characteristic curves, where we really only need those two directions if we have an augmented descriptor. Okay, so that example already shows that they're not equal, right? If we're comparing cardinalities this way. Yeah, okay, so if they're not equal, then why would the inequality point this direction, right? And there are a couple of reasons why I believe that to be true. So the first is that faithful sets of non-augmented descriptors, so including non-augmented persistence diagrams, they really rely on the flatness of the simplicial complex. So that's where, when I had that list of related work, that Curry et al. Paper had that bound on curvature, the bound on flatness. That's exactly why they needed that, as they were using non-augmented persistence diagrams. And then this last bullet point is a really related idea. We can show that if we have a faithful set of a non-augmented descriptor, there's a certain requirement we have for every maximal simplex. So maximal simplex is, it's not the face of anything higher dimensional, right? And for every maximal k-simplex, we can show that we need descriptors generated from d minus k perpendicular directions, where d is whatever space our complex is embedded in. Okay, let me illustrate this last bullet point. Let me flesh it out a little bit more. So related to this idea of a non-augmented descriptor requiring lots of perpendicular directions. Why would that be? Okay, so let's suppose that these two are separate simplicial complexes, but they sort of are embedded in the same location. I've just drawn them separately so we can visualize it, right? And let's think in terms of non-augmented persistence diagrams, since that's probably most familiar. Okay, so the question I'm going to ask is, from what direction would we be able to detect a difference in these complexes, right? So what directions would produce a distinct persistence diagrams, non-augmented? So here's a non-example, right? If I come down from this direction, I see a connected component born in each case, and then no other event, right? So they would produce the exact same simplicial complex. So far I haven't been able to distinguish the two. Similarly, if I come up from this direction, right, you can kind of see that the same thing is happening, right? I see a single connected component born in both of the left and the right. These are kind of different situations, remember? And I can't distinguish the two. So what direction would distinguish the two? Well, here's an example of one, right? I need to essentially come perpendicular to this edge of this pair of vertices, right? And now, what is the difference? On the left here, I would see a single connected component born, whereas on the right, I would see two connected components born that are later, one dies as they merge at this third vertex height. So finally, I've identified a direction that produces different descriptors, right? Now notice if I were in the world of augmented diagrams, since I know I have an event at the height of every vertex, this problem is not existent, right? So any of these directions would have different augmented descriptors or augmented diagrams. So that's where that d minus k perpendicular directions comes from. Okay. Okay. So if it were true that that our persistence diagrams, this should be a strict inequality, sorry, is strictly less than augmented Euler characteristic curves, this would actually give us then a total order on our set of 6. It sort of separates the non-augmented from the augmented, and gives us this this total order, which would be nice. I'm pretty sure that other inequalities in this line can be made strict. The Euler characteristic and Betty curve in particular, I suspect we can find an example where the minimal faithful set for Euler characteristic curves is greater than the minimal faithful set for Betty curves. And that's sort of work in progress. So in general, right, how would we go about showing these results, right? They're sort of tricky to prove because they deal a lot with minimal sets of things, and it's showing that something actually is minimal it can be a challenge. So if I wanted to show this conjectured inequality, that persistence diagrams are strictly less than augmented Euler characteristic curves, there are a couple possible proof strategies. So one kind of naive way, but perhaps a good starting place is to start with some faithful set of persistence diagrams. Great, so we know that it has properties about being perpendicular to maximal simplices. So we kind of have a sense for the size of the thing in relationship to the number of the number of maximal simplices. And then maybe the strategy could be, naively, maybe we want to look at the set of augmented Euler characteristic curves taken from that exact same set of directions. And perhaps that it can be shown that that set is faithful. That would be one way to attack this conjectured inequality. A little more nuanced would be to start with a set of persistence diagrams, transfer over to augmented Euler characteristic curves, and then kind of switch out, swap directions so that you still have a sort of known cardinality, but maybe you're able to control a little bit more about how you prove that it's faithful. And then, yeah, just in general, the fact that persistence diagrams are dependent on the number of maximal simplices, whereas the augmented Euler characteristic curves are not, feels like a really strong statement and perhaps a powerful tool in attacking this conjecture. Okay. Yeah, so I'll just end with some closing thoughts and interesting questions that I see as ongoing work. So one is, how small could a faithful set be? So if you look at simplicial complexes generally, this is lower bounded by D diagrams. This is, I guess I didn't write specifically for augmented descriptors. But it's currently a little bit difficult to prove much about minimal faithful sets. One surprising thing that we've seen come up is when we're dealing with augmented descriptors, in the situations that are small enough for us to understand, we often see the number 2D minus 1. Remember, D being the dimension that our complex is embedded in. We often see that number come up as the size of a minimal faithful set. So for a while, we actually believed that that was the size of a minimal faithful set. And then we eventually found this counterexample. So if you look at, say, augmented persistence diagrams, a faithful set actually requires a number that depends on the number of vertices. So you can kind of extend this pattern out and require more and more augmented persistence diagrams. So that's kind of an interesting thing that I'd like to understand better. Yeah, so with that, I have some references, and I'm happy to take questions.
Yeah, thanks, Anna. That was an interesting talk. Are there any questions for Anna? Yeah, so I have, so I was wondering if you've looked at any multi-parameter persistence-based invariants and how those fit into this Poset structure.
So there was a time when I thought about it, but I haven't really pursued that. I think it's definitely an interesting question, right? So we have this idea of the PHT where you're taking a single direction as your parameter. But what would happen, say, if you're taking pairs of directions, right, as your biparameter filtration, right? Yeah, I guess the only thing I have to say is I think that's a really super interesting question, and I just haven't thought about it yet. But yeah.
Yeah, are there any other questions for Anna? Yeah, so I have another sort of, I don't know if this is a dumb question or not, but is there like, is this set of descriptors, is it finite, or can you consider, or this poset of descriptors at least, is it, it seems like it could possibly be finite.
That's interesting, yeah. So I've chosen to focus on these 6 descriptor types in large part because they're the most popular, but you really, depending on how you choose to define the broad notion of a topological descriptor, you could try to compare some crazy things, right? I think one issue is that it's no longer necessarily the case that a faithful set exists. For example, maybe your descriptor reports back the bottom vertex in any direction. Well, that's never going to be faithful, right? You might have all sorts of interesting stuff going on the inside. So perhaps that's a poor notion of topological descriptor, but I think maybe at the heart of that question is, what do I count as a topological descriptor?
I see.
And what do I not count? Yeah.
Huh.
One more comment on that, I guess. There could be perhaps a way to include the notion of sort of the non-existence of a faithful set into the relation. So perhaps if you have a topological descriptor type that never will have a faithful set, you could sort of declare that to be minimal. That's sort of one way that we thought about getting around that issue. But by restricting ourselves to these 6 descriptors, which are known to always have faithful sets, that's another way of getting around that issue.
I see. Yeah.